Hello guys, today the last topic of first chapter, the electric forces and field. In our last class, we discussed about electric forces, how charges repel, attract each other, the Coulomb's law and its various variations. Today we'll wrap it up with electric field or electrostatic field. What is electric field? Now we know that there is a charge. There will be some extent or some space, some distance up to which this charge can attract or repel any other charge, right? So there has to have some particular space about it. So that is what electric field is. The region or space about a charge within which its electrical properties can be experienced. This is the meaning of electric field, not the definition. Electric field is the region or space about a charge within which its electrical properties can be experienced, and it is defined as force experienced per unit charge. What's a unit charge? As the name suggests, unit magnitude 1 charge, unit charge. Now in our electrostats, when we deduce any expression, when we do any equation for electric force, field potential, we always tend to take a unit positive charge or test charge. They all mean the same. It is the smallest charge possible which do not affect the electric field or potential or the force of any other charges in its vicinity, and we use such ideal charge to derive our expressions. So for now, force electric field is what? Force experienced per unit charge. Force experienced per unit charge. Let's say this is our source charge. Here at a distance r we have placed our q0, which is our test charge. So accordingly, force between those two charges would be, as we discussed in our last class, 1 upon 4 pi epsilon naught q1, which is this charge, q2, which is that test charge, upon distance square whole upon q0. This gives me the equation for electric field, which is 1 upon 4 pi epsilon naught q upon r square. Simple. Now note this thing. Force is a vector quantity. Electric field must be vector quantity. So what happens when we define or derive an equation for any vector quantity? Is there any change in the equation? For example, we just deduce an expression for electric field, which is what? 1 upon 4 pi epsilon naught q upon r square. This is the charge due to which electric field is present. This is the distance at which we are obtaining the value of electric field. See this formula. F is equal to q naught E. Where did this come from? The same equation, E is equal to F upon q naught. Take this that side, F is equal to q naught E. Or F is equal to q naught E. This statement is absolutely right in terms of vector notations. But in electric field, okay, I am giving you two options. Find out which one is correct. Number 1, electric field is 1 upon 4 pi epsilon naught q upon r square unit vector r, or electric field is 1 upon 4 pi epsilon naught q upon r square into r upon r. That means this r into r becomes, this thing becomes cube. So just think which of this formula is right. Exactly, both are right. How? When you derive its value, do we have, this is our region, this is our source charge. I am finding the value of electric field at this point. For that, what we did, we placed a test charge here and we obtained an expression using this formula, that is electric field is force experienced per unit charge. This will be the direction of electric field. If you are still confused or you are still thinking about what is the direction of electric field y, just leave it for now. Electric field is F upon q naught, right? Taking vector sign, electric field will be in the direction of force because both are represented in this equation. Where is the force? Q naught is placed here, it will be experiencing a force outward direction, so that will be the direction of electric field. Now this equation, I represented electric field in vector form. That means what? Magnitude as well as direction. Magnitude k cube on r square, that is right. The direction r cap, this is the distance. What is r cap? It is along r, unit vector along the r. That means it will be also outside, outwards. Unit vector just gives us the magnitude and direction. What? It just gives us the direction, not the magnitude. Its magnitude is 1. So right now our unit vector r cap is in this direction, so this equation is satisfied. Now what is a unit vector? In 10th, last class you did an detailed about unit vectors or vectors. What was it? Unit vectors is defined as a vector divided by its magnitude. This was the formula for unit vector. So I have just replaced this with this over here. Vector electric field, the vector electric field, that is field plus magnitude plus direction. This is the magnitude part. The direction r cap, that is vector r upon magnitude. Magnitude got multiplied here, so both the formulas are right. Will it make any difference if you draw a graph between electric field and distance if you use this formula and this formula? You can see electric field is inversely proportional to distance square. Here electric field is inversely proportional to distance cube. Will it make any difference while obtaining the graph? Answer is no. How? Because while obtaining the graph you will be taking the either this formula or you will take the unit vector, which is that formula. So this is the unit, this is all about electric field. Now how do we represent electric field? Electric fields are represented by electric lines of force. So what is this new term? Electric lines of force. Electric lines of force. These are imaginary paths which represent the direction of electric field. How do we do it? How do we make those imaginary lines? According to definition, these are imaginary paths along which a point charge will move if it is free to do so. These are imaginary paths along which a point charge will move if it is free to do so. For example, there is a very big charge here. I am putting my point charge here, or the test charge, unit charge, call it by any name. Will this positive charge be repelling this charge in this direction or straight outwards? Exactly, straight outwards. So what are you left with? This would be the direction of force. So if this point charge is free to move, it will move in this direction. If the point charge is here, it will move in this direction. If it is here, it will move in this direction. So these are the directions of the path which a point charge can take. So accordingly, these are electric lines of force, as these are imaginary paths. So for the last time, what are electric lines of force? These are imaginary paths along which a point charge will move if it is free to do so. So suppose you have a negative charge. How will be these electric lines of force or negative charge? Place a point charge, unit charge, test charge, they are always supposed to be positive. So it will get attracted towards the negative charge. Normally inverts, vertically inverts, radially inverts. They all mean the same. Radially inverts means, suppose you have a big sphere. That sphere must be having some radius. Extend the radius. That will be called radially outwards or radially inwards. Now from here, if the point charge is here, it will be attracted vertically inwards, normally inwards. So these are the directions of electric lines of force for a negative charge. This is how we represent electric field. We have a positive. For positive, these are normally outwards. For negative, these are normally inwards. What if we have a system of positive negative charge? Let us just discuss this while we are discussing the properties of electric lines of force. Note all of these points. This is a very important question for your boards. Properties. I'll be writing a I'll be writing the main properties, the key points here, and I'll be explaining the diagram here, and whatever you have to write, I'll be speaking it. So keep your mind here. First one, these are normally outwards and normally inwards. These are normally outwards for a positive charge and normally inwards for a negative charge. What if you have a positive negative charge system? So second point, for a positive negative charge, for a positive negative charge system, which is this, how do you think will this charge, okay, stop writing and listen, how will you think that this charge is going to behave in this system? It will, yes, it will get repelled by this positive charge, it will get attracted towards this charge. So in which direction should it move? Should it move in that direction or this direction? These are two forces, that means it will move in the direction of resultant of these two forces over here. Once it has done some distance, these directions of force will again change, for positive here, for negative inside. So again its motion of direction will change. So consequently it will take a curved path. So this is how electric lines of force are for a positive negative charge system. These are closed continuous curves which originate from a positive charge and they terminate on a negative charge. If you have skipped the point, write it down. For a positive negative charge system, these lines originate from a positive charge and terminate on a negative charge. 2 points. Third, direction of electric field at any point on the curve is given by drawing the tangent at that point. I'll repeat it. The direction of electric field at any point on the curve is given by drawing tangent at that point. Suppose this is the curve of electric line of force. We have to find electric field, the direction of electric field at this point. Draw a tangent here. This tangent will give you the direction of electric field at that point. Let me go back to the previous point. What was it? For a positive negative charge system, these are closed continuous curves. This thing, closed continuous curve. This point has been asked in different ways in our 1 marks question in boards. Can electric lines of force be discontinuous? Can they vanish at certain point? Or is it mandatory for electric lines of force to be closed path only, not the broken paths? What could be your answer? Answer is simple. No, they are always closed continuous curves. What is the logic behind it? You have a positive charge here, you have a negative charge here. Drawing electric line of force means you are actually making the imaginary path along which this point charge will be going to move. From positive it is going to be get repelled, from negative it is going to get attracted. So this charge is going to take this path. But obviously this charge is not going to vanish from here and appear back here and go to there. That means this path can't be in broken state. So it has to be closed and continuous. Alright, let's come to the tangent point, which is clear. Direction at any point is given by tangent. So this property gives rise to another very unique property, that is, two electric lines of force never intersect each other. I am writing only the key points here. You have to write the full statements if you have asked. Two electric lines of force never intersect each other. Why? Suppose we have these two lines. At this point of intersection, I can draw two tangents. let me redraw this. At the point of intersection, I can draw two tangents, one for this curve and one for that curve. That means I am having two directions of electric field at the same point, which is not possible. Why? Why is this not possible? It is written in the book. You have heard it from the teachers as well that it is not possible. Why? It's a very simple logic. Because electric field is a vector quantity, there can only be one possible direction at any single point. That is why there cannot be two different directions of electric field at the same point. Okay, two lines never intersect each other. Then density of electric lines at any region gives the strength of electric field at that point. I sometimes wonder it's difficult to write something else and speak something else at the same time. Density and strength, what does this point states? I am having electric lines of force like these, and they tend to converge in this region, and they tend to further converge in this region. Let us say this is region A, or this is region A, this is region B, this is region C. The point was the density of electric lines of force gives the strength of electric field at any region. That means where is the density maximum? At C. Therefore, electric field at C is greater than electric field at B, which will be greater than electric field at A. Simple. Next point. They contract longitudinally. That's it. That's the point. They contract longitudinally. In brackets you can write they contract longitudinally on account of attraction between unlike charges. Unlike charges attract, like charges repel. So on account of this attraction, the electric lines of force tend to converge along the longitude side. So they are very close to each other. More the distance you cover on the equatorial part, there will be more distances between the electric lines of force. That's the point. They contract longitudinally. In brackets you can also ask, give the reason, because or on account of attraction between unlike charges. Last point, they exert lateral pressure on each other. They exert lateral pressure on each other. That means, okay, you can also write in bracket on account of repulsion between like charges. Suppose this is a positive charge, this is a positive charge. We already know that for a positive charge, electric lines of force will be vertically or radially outwards. Similarly for this particular charge as well. So what will happen at a region here? What will happen at this region? Electric lines do not converge, they do not intersect. So at this region, they tend to force each other apart and they will push each other apart, but they will not intersect. So there will be a region of null point. Null point means there will be no electric field. So that is why the point, they exert lateral pressure on each other and tend to move away. These are the properties of electric lines of force, and we are moving on to next topic. What is it? The electric dipole. What is a dipole? In your books, help books, you have heard about this statement of electric dipole, which is what? Two equal and opposite forces separated by a very small distance.